Okay. Aiden. All right. Jen. Yep. Brenda. Jacqueline. Yep. Leaf. Daniela. Yvonne. Okay. Jasmine. Okay. Jara. Haley. No. Christian. All right. Cynthia. And Nadia. Okay. Najma. No. Miro. Yes. Brindley. Yes. Levi. Yes. No. Isha. Rocio. Yes. All right. All right. All right, ladies and gentlemen. So today we're going to be doing an activity in the lab in just a few minutes. Okay. We've got a few things that we've started that we're working on that we're going to get to and we're going to do. If we have time, we'll go back to lab safety today. Otherwise, I'll finish it up tomorrow. Okay. We are doing a Alka-Seltzer lab today. The lab is in your Google Classroom. We'll go to it in a minute and start looking at it. Okay. Yesterday, we took some time and we looked at some vocabulary terms. And two of the terms you looked at were qualitative and quantitative observation. Okay. So what is a qualitative observation, ladies and gentlemen? What does that mean if it is qualitative?
Qualitative was no numbers.
Okay. Okay. Qualitative was no numbers. Quantitative was numbers. Now, this is a good thing because very few things in science are black and white. It's this or it's this. But observations are that way. If there is a number in an observation, it is a quantitative observation. If there is no number, but you are still describing like a quantity, the object is large, the object is big, the object is tall, the object is long. Without numbers, it still is qualitative. Has to have a number in it. So give me an example of either a qualitative or a quantitative observation. Make one up. Nadia, go ahead.
There's 15 people in the room.
Okay, 15 people in the room. Good. Haley.
The desk is brown.
The desk is brown. Good. Lee.
Yellow pencil.
Yellow pencil. Good. Jara.
Pink paper.
Pink paper. Okay. Rocio. What?
Wait, what are they?
Describe either a qualitative or a quantitative observation. Just make one up. It doesn't even have to be accurate.
A telephone.
Okay. Describe something about it.
A handle.
Okay. What color is it?
Black.
Okay. So again, when you say an object that isn't really describing it, okay, so we want some description of it. It's black. It has 12 keys. What would 12 keys be?
Quantitative.
It would be a quantitative observation. Okay. So there are ways you can describe things to be quantitative or qualitative. What about bluebirds, Levi? That's qualitative. What about 17.5 grams, Jim? Quantitative. If it has a number in it, it's quantitative. If it doesn't have a number in it, it's qualitative. Okay? That is always the way it is, ladies and gentlemen. That is always the way it is. Okay? Now, today you're going to be taking some observations in your lab. You're going to be taking some qualitative. You're going to be taking some quantitative. Okay? Both have value, ladies and gentlemen. But we will get into talking a little bit later about which one is a little bit better than the others. Okay? So that is what we're going to be doing today. So that was our introduction to it. I am going to finish up lab safety here real quick, ladies and gentlemen, because this is where we were at when we left yesterday. So you don't have to have your computers open right now. You can leave them open. That is fine, ladies and gentlemen. But let's finish up this little bit of lab safety, okay? Number one, like today, don't start a lab until you're instructed to do so. I'm going to give you some instructions. I'm going to go over some things with you. I'm going to remind you of some safety things and things like that. So if we are doing a lab and it takes 2 days, I may tell you, okay, tomorrow when you come in, you can go right back and you can go to work. Well, you've been instructed to do so, okay? But if not, please wait until we tell you to do so. Make sure you understand the lab and the instructions. If you don't know what we're doing or a part of it or something about it, please ask. I will be more than happy to answer those things for you. When you get back to the lab, just kind of look things over and make sure that the things that you're using, the things that you have out there, ladies and gentlemen, there's nothing that appears to be out of ordinary to it. There's no cords that are like, showing bare wires. There's nothing chipped or broken or things like that. I will never leave you chipped or broken glassware. That doesn't mean it won't be there. It means I will never leave it for you, okay? Especially if we're doing a lab a couple days in a row. It is possible that something breaks and somebody leaves it there. If you get to it the next day and it's broken, please let me know and I'll get you a new one, okay? And believe me, glassware breaks. You do not have to do anything wrong. You don't have to be messing around. You don't have to do anything that screws up glassware. Just sometimes breaks. Now, if I take a glass beaker and I throw it at Miro and it breaks in the process, that's a little bit different, right? So again, let's be smart about things. If you're unsure how to use equipment or what to do, let me know, and use goggles when there's heat, chemicals, or glassware involved. Today, I'm not going to make you wear goggles for the lab that we're going to do today, okay? So just please be careful, okay? We always waft to test for an odor. You hold it out in front of you, you put your hand above it, and you wave it at your nose. If you could smell something, great. If you can't, you could always move it closer, okay? Real important thing, people with smells especially will always try to describe them. Telling me that something has an odor is descriptive enough. That there is an odor present is good. If you can describe it, it smells like burning sugar. Okay, great. But otherwise, just tell me that there is an odor present, okay? Use the back of your hand to determine if an object is hot. Any idea why you use the back of your hand?
The front of your hand more sensitive.
Actually, the back is a little bit more sensitive than the front, only because most people have like calluses and things built up on the front. And that is one of the reasons. But the other reason is this. Your body works on electrical impulses. And when you give it an exterior stimulation, sometimes it will react. And normally your body's reaction to things is to clench up. Okay? So if you're like this and this object is hot, you're going to clench up and you're going to be holding it in your hand and maybe not be able to set it down for a second. But if you come at it with the back of your hand, your natural reaction is to pull you away from it when your body clenches up. So use the back of your hand. If you could feel the heat from it, don't get any closer. If you can't, now you can gently touch it, okay? But again, we're just doing it safe as possible. Matches and other flammables go in the tin cups that are at every station. There is a cup like this at every station. Please, when we're using matches, blow them out and put them in here. Blow them out first, okay? I've seen people throw lit matches in here. And if you're not the first one using matches that day, there may be 4 or 5 in there. Now we've got a small bonfire going in here that we could cook s'mores on. And people will panic and go grab this to take it to the sink, and it will be incredibly hot in a very short period of time. So if you do accidentally throw a burning match in there, just leave it. Just leave it. I'll come over and I'll put something on it to smother it, okay? But please put the matches out. Don't blow them out and let them sit on the counter. Don't throw them in the trash cans, okay? Put them in there, okay? Do only instructor-approved labs in the classes and dress appropriately. Again, we are going to be working with some chemicals that are very dangerous. And if you go and mix those things with something else, you're going to get a reaction that we don't want. There's probably a reason I don't want you mixing certain things together. So please don't try that on your own and see what happens, okay? So dress appropriately for the lab. Okay, that means no open-toed sandals. Well, at this point in the year, that really probably isn't much of a problem for us, okay? No long dangling jewelry or clothes, okay? So again, if you have a hooded sweatshirt on, absolutely nothing wrong with that, but you may want to tuck the strings in. If you have an ID on, you may want to take that off, or you may want to tuck it into your shirt just so that it doesn't dangle into something. We say no contact lenses. I wear contact lenses every day, ladies and gentlemen. Okay? The easiest way to protect yourself is to wear your goggles when you're doing that. But please understand, if something ever does get in your eye, one of the things that we have to do is get your contact lenses out. And if something like acid or something like that gets in there, which should not ever happen to you if you're wearing your goggles, but if it does, it can cause the lens of your contact to fuse to your eyelid. Fuse to your cornea, I should say. Okay? Not a good feeling, ladies and gentlemen. Long hair tied back. Okay, I don't have this problem, but if you do, I have hair ties for you as well. Okay? Now, for today's lab, you're not going to need to tie your hair back. We're not working with open flames. We're not working with chemicals that are going to set your hair on fire. I suggest older clothes because sometimes we're working with things that will stain, but I always have lab aprons in the back, okay, for you to use, okay? Please understand, you can do nothing wrong and an accident can happen in the lab. We're boiling water in the back of the lab today, okay? I had a 2-liter beaker up here one day. We were boiling water with it. I was talking in front of the class like this. We heard ting, and we looked, and the entire bottom of the beaker broke completely around. And all 2 liters of water came splashing out on the desk and splashing out onto me. Luckily, it wasn't boiling yet. But if I had had open-toed sandals on that day, you could burn your feet really bad. Didn't do anything wrong. It just happens. When you heat and cool glassware, when you use it over years and years, it gets brittle, it gets weak, and sometimes things happen. Okay? After you're done, we ask that you clean up. Don't leave paper towels and things laying on your desk. Wipe it up if there is water. There are sponges and things at every station, ladies and gentlemen. Okay? Put all your equipment back in the proper place. Please don't take things from one lab station and move them to another. If there is something that you need that is not out at your lab station, please ask and I will get it for you. Because if you move it, then the next person who comes in who needs it will not have it. Okay? Dispose of waste properly. A lot of our waste can go down the drain. What you're doing today can go down the drain. What we're doing a week from now may not be able to. And I may have containers out in the middle where you have to take your things and put them in there. Because then I have to dispose of them properly. And always a good idea, ladies and gentlemen, to wash your hands before leaving the lab area. There are going to be things that you could touch and you could feel to make observations of them. But I sure wouldn't want to go eat a sandwich then afterwards before I wash my hands. Okay? Not that it is unsafe for you to touch, but touching and ingesting are 2 very different things. That's why we ask you to wash your hands before you leave the lab area. All right. So that's it on lab safety. Any questions? Okay? Here is the biggest thing. If there is an issue, call me over. Call me over. If it's something you can clean up, I will tell you. If it's something that I need to help you with, I will tell you. If it's something that we break glassware or whatever, we'll fix it. Okay? All right, ladies and gentlemen, please open up your computers and get to today's lab. It is in the Google Classroom. It is the Alka-Seltzer lab here. Please click on it and open up your document for it, ladies and gentlemen. Open up your document for it. I don't have mine open. Sorry about that. All right. So here's our lab, ladies and gentlemen, for today. Okay. I told you this the other day. Yellow boxes are things that you need to fill in. So I'm going to grade this lab. When I grade it, it's worth 25 points. Lab is going to be due tomorrow. You're going to work on it today. I'll give you time to answer the questions at the end, time to collect your data and things. Then you have to turn it in. Now, again, the deadline is tomorrow by the end of the day. If you get it done today, turn it in. Get it out of the way. Okay? Get it out of the way. Get it turned in. Okay? How will changing the temperature of water and type of liquid affect the speed in Alka-Seltzer tablet, the speed of an Alka-Seltzer tablet dissolving, and learn to apply the vocabulary from the unit? So the vocabulary that we had you do yesterday on your slides is what we are going to use this experiment for. So tomorrow, later today, depending on how far we get, we are going to talk about a hypothesis. We're going to talk about an experiment. We're going to talk about a quantitative and a qualitative observation. All those things that you took notes on yesterday. And there was that third column, that green column. We're going to give you an example from the lab. Yes? Right there, if you got your cord. Okay. So again, ladies and gentlemen, the idea of this lab is to introduce things to you and also to introduce the vocabulary that we are talking about that we're going to quiz you on later this week. Okay? So we need to write a purpose for this lab. Okay. So how will changing the temperature of water and type of liquid affect the speed an Alka-Seltzer tablet dissolves? Okay? That's what we're trying to do here. So we're going to turn that into a purpose. Okay? So our purpose is, get to see my wonderful typing skills, to find out how, that you need to start copying this in, changing the temp of a liquid or type of a liquid determines how fast a reaction will occur. That is what we are doing in the lab today. Right? That is what we are doing in the lab today, ladies and gentlemen. I just need to turn down my water here real quick. Congratulations, you just got 2 points on your lab. And all you had to do is copy down that purpose. All right. Questions? All right. So let's go down. Now, my definition of an experiment in this class, ladies and gentlemen, is a carefully controlled series of observations. That's what an experiment is. A carefully controlled series of observations. So what we have here is we have what we call a 2-column format. Here's your procedure. Here's the steps that you do. And then there is a place for you to record the observations that happen during those steps, if there are any. Not every one of these steps requires you to make an observation, but many of them do. Okay? So I give you the procedure, and then I tell you, okay, over here is where you make your observations. So that's how we get our definition of a carefully controlled series of observations. So we're going to start out by making qualitative observations. Qualitative means, again, no what?
Numbers.
No numbers. Okay? So in here, I have a table set up for you. And you'll notice, minimum 3, 4 or more are recommended. If you want to do more than this, you could, at the end, hit the tab button. It'll put another row down below. You are welcome to do that. But the minimum requirement is to make at least 3 observations. Now, the reason I suggest 4 is because occasionally people will do something like the liquid is clear, the liquid is, or it's clear, it's a liquid, it's transparent, and it's clear. You told me clear twice. Okay? Now, if you do that and you only take 3 observations, you're not getting credit for giving me the same observation twice. So if you put 4, you've got an extra one there in case. If you only want to do 3, that is fine. So in here, you're going to take a look at water, and you're going to make some qualitative observations. Now, qualitative observations require us to use our senses. We rely on sight tremendously. Getting you to describe what you see is normally not a problem. Okay? You can also use your sense of smell. Now, if there is no odor, you can write down no odor. That is still an observation. If there is an odor, write down that there is one. You can use your sense of touch. Okay? Everything in today's lab you can touch. You want to feel the water? You want to feel the 7-Up? You want to feel the Alka-Seltzer? Please feel free to. Okay? When you're describing how something feels, we could talk about smooth, sticky. We could talk about slick. We could talk about rough. We could talk about grainy or sharp. Any of those things. Any way you can describe how something feels. Okay? Hopefully the water is not speaking to you. If it is, please let me know and I will get you the help you need. Okay? So nothing in the lab should be talking to you. However, during the reaction today, you may hear sounds. And during a reaction, if you hear sounds, you can write them down. Hear a fizzing sound, hear a bubbling sound, hear something like that. Please then write those down. Okay? The one sense you are not allowed to use today, even though it would be very safe to do so, is taste. We do not taste anything in the lab unless you are instructed to do so. Now, it is not that I don't believe you can taste 7-Up. You could. It's not that I don't believe you can drink water. You can. What I don't trust is the glassware that I have out in there that is had other chemicals in it and things like that, that it's clean enough to drink out of. So again, please don't taste anything today. Okay? So we covered sight, we covered touch, we covered smell, we covered taste, and we covered hearing. That's it. You just need to make 3 observations of the water, the Alka-Seltzer, and the 7-Up. Okay? And you make them before you begin anything. So at your station, ladies and gentlemen, there is a packet with 2 Alka-Seltzers in it. Open it up, take it out, and check them out. Okay? Now, in mine, one of them is broken. That isn't going to work. We're going to have to get rid of that one. Okay? Because if we use one that is broken and one that is not, what does that do to our experiment? It adds a variable, and we do not want to do that. So in the back, in the middle, there is a whole box full of Alka-Seltzers. If you need a new container or a new packet of them because one is broken, just take that one, leave it for me. There are some labs that I can use broken Alka-Seltzers for, but for this one, you need a whole one. Okay? All right. Place 100 milliliters of room temperature water into a 250 milliliter beaker. That is what we are going to do together. Sorry, I meant to grab a container of water earlier, and I did not. So let me grab one now. At the stations, ladies and gentlemen, there are bottles like this and bottles like this. Both of these contain something called deionized water. Deionized water is water that has literally had certain ions that common water will have in it removed. Green Bay, when they treat water and send it out to our homes, ladies and gentlemen, they add chlorine to kill bacteria. They add fluorine for your teeth because it is good for it. The problem is chlorine and fluorine react with a lot of chemicals. So we want to take those out. So the water that is in these containers comes from the jugs that are up on the top back there, ladies and gentlemen. If you ever need to fill one, please feel free to. But this water is what is called deionized water. And what that means, ladies and gentlemen, is it is water that has had certain ions that might react with chemicals removed from it. Okay? So we're going to put 100 milliliters of room temperature water into this container. Now, first of all, what is this for? What is this thing? What? Pouring? It's actually not for measuring. It's not for pouring. Here's what it's for. That. If you knock this over, this ring at the top is designed to hit the counter first so we don't chip or break the top of this because these are about 20 bucks a piece. Okay? I know it's ridiculous, but that's what they charge us. So the reason that is on there is so that if you accidentally tip it over, it hits the counter first and it probably will not break. Okay? Now, the other thing is the reason this is not round is so that when it hits the counter, it doesn't then roll off the edge. So, a couple things for safety there. This doesn't work very well if you do this to get it out of the way so you can see at the top. Okay? So please leave this up near the top so that it will not break if you accidentally tip it over. To measure 100 milliliters of liquid, ladies and gentlemen, you get to see my wonderful drawing skills right away. I am a lousy artist. Don't make fun of me. Okay? Water always does this weirdly unique thing, which is it has what is called a meniscus. Meniscus is this rounded shape that it always has. And that is because literally the water on the edges is clinging to the glass container. And the middle, it is not. So when we read this, ladies and gentlemen, you want to read this to the lowest part. Okay? That is the level that the water is at that tells you, okay, here's how much is in there. Now, the other thing you need to do when you do this, ladies and gentlemen, is you need to get to what we call eye level. Now, there are 2 ways you can do this. You can bring this up to your eye. Not a good idea. Or you can bring your eye down to it like this, ladies and gentlemen. And the reason for that, we need this flat so that we can read the lowest part of the meniscus. On the table, it's going to be flat. So I'm going to take and I'm going to pour some water in here. Now, when you get close, ladies and gentlemen, you have a couple of options. You could continue to pour out of the pitcher if you wish. A better option is to grab this bottle and use it because it will dispense a lot less at a time until you get to 100 milliliters. The bottom of my meniscus is reading right at the 100 milliliter line on here, ladies and gentlemen. So now I have 100 milliliters of room temperature water. Now, you will not have to do room temperature water. We're doing this all together. Okay? All of us are doing this together. I've made my observations. I've made my observations of my Alka-Seltzer. We're now going to take and put the two of them together, and we are going to begin timing. When you go to your station, there is no stopwatch out. However, there is a drawer when you are standing at your station. There are two doors at the top. Those have nothing in them. The hot plates are already out. And then there are drawers down below. There is one big door in the middle, and there are two sets of drawers down the side. One of them is marked lab equipment. If you slide that drawer open, you will find things like clamps. You will find test tube racks. You will find hot hands. You will find all kinds of things. One of the things you will find in there is a stopwatch, ladies and gentlemen. Take it out. Okay? And what we're going to do is we're going to take and we're going to put the Alka-Seltzer into our water, and we are going to time how long it takes to dissolve. So we're going to have our stopwatch ready. We're going to drop this in, and we are going to time it. Now, along with timing it, ladies and gentlemen, you are also going to record what you see going on in that container, what you hear going on in that container, what you smell going on in that container. Okay? You are going to make another set of observations for the water and Alka-Seltzer reacting. You're going to make observations for the 7-Up and the Alka-Seltzer. I don't care if you use hot water. I don't care if you use cold water. That choice is yours. Either one. Okay? So you need to make some observations. Now, I am also watching, ladies and gentlemen, for the tablet to dissolve completely. And as soon as that tablet is done dissolving completely, as soon as I no longer see the tablet in there, ladies and gentlemen, I'm going to stop my timer. Now, we will all use the same room temperature water and Alka-Seltzer that I am doing right now. So in a minute, when this is gone, now it's floating on the top. As soon as this is gone, ladies and gentlemen, I will stop the stopwatch and I will give you a time. I'm doing it until the entire tablet is gone, ladies and gentlemen. Okay. Why is my stopwatch not stopping? Anyway, I did see the time. Sorry, my stopwatch is not stopping. Okay. The time, ladies and gentlemen, and we all need to copy this down. In this blue box here was 1 minute. Then we use the colon button. 27.35 seconds. You need to put a unit in there. Our unit is, well, let's not put seconds. Why? Because time is unique, right? Time is weird. This is a combination of what units? Minutes and seconds. Normally, we would put a unit there. I'm not going to do that because this is a time, okay? If anything, we would have to do minutes and seconds, but we're not going to do that, okay? The colon means this is the unit of minutes, this is seconds, and this is literally tenths and hundredths of a second. And that's what your stopwatch will read to. Now, yours will stop. Mine did not. Sorry about that, ladies and gentlemen, okay? All right, so now we've all got this done. We are going to compare what happens when we use hot water, when we use cold water, and when we use 7-Up to when we just did this one. So you're going to get three other readings. One with hot water, one with cold water, one with 7-Up. Okay? So at your station, there are 3 packets of Alka-Seltzer for the 2 groups to use. That gives you 6 Alka-Seltzers, 3 for each side. Both of you doing hot water, both of you doing cold water, both of you doing 7-Up. Okay? I don't care which order you want to do them in. That is completely and entirely up to you. However, because we have the hot water and the cold water in the middle, because the hot water is more difficult to handle, what I'm going to ask you to do is, when you're ready to do the hot water, by the way, when I'm done with this, down the drain, rinse this out a couple times. It's ready to go. When you go to do the hot water, please bring this over to me. I will give you more than 100 milliliters of hot water. You can go back, you can get 100 milliliters into here, dump the rest out, and then pour it back from there into here and get going on your lab. With the hot water and the cold water, you need to try to work as quickly as you can, because the hot water is going to cool down as soon as we take it off the heat, and the cold water is going to start heating up as soon as we take it out of the ice. Okay? The soda you have more time with. So you can bring your graduated cylinder over if you want to do the cold water. If you want to bring this over and get more than 100 mils and do that same process for the cold water and the 7-Up, you are welcome to. Okay? Questions? Okay. So again, the procedure is there. Tells you exactly what to do. First thing I would do, though, take your observations of the water, the Alka-Seltzer, the 7-Up. Then I would take and start the experiment, getting 100 mils in, dropping an Alka-Seltzer, and starting your timer. Please remember, when you're doing water and seltzer, write down what happens. When you're doing 7-Up and Alka-Seltzer, write down what happens. These may be similar. I expect them to be. You do not need different observations here that you do here. The same way, if water is clear and 7-Up is clear, you can put that down for both. Okay? You can use similar observations here and here, ladies and gentlemen. That is completely fine. Okay? They do not have to be different here and here. I think they're going to be different here, though. Okay? Questions? All right. The way the lab works, ladies and gentlemen, 2 people on one side are a lab team, 2 people on the other side are a lab team. We have stations set up in the back of the room, the last 2 stations on each side, because that should be enough to cover us, because I think we've got like 16 people in here. 4, 6, 8, 10, 12, 14, 16, 17. Okay? 17 people. So again, everything is out there. There are no, for this lab, no groups of 3. Okay? Actually, sorry, we got 17 people. We can have 1 group of 3. Okay, 1 group of 3. That group of 3 will work over here at this station right behind Leaf right there. This one station right here where there is only 1 setup. That's where our group of 3 will work. Otherwise, all our groups will be groups of 2. You want to pick your partners, or you want me to?
You can pick.
Yeah, I've never had a class actually let me pick their partners. So, okay, I'm fine with that. Okay? All right, let's go. Let's get to work, ladies and gentlemen. In this section, need to be filled. 3 of the 4 boxes down here need to be filled. And you should have times in each one of these. Now, real important thing, and I probably should have told you this before, but we'll get into this as we go on. All of your times, ladies and gentlemen, all of them should be to the decimal and 2 places beyond it. So if you have an instrument and it ever reads like 0.00 at the end, do not drop that 0.00. In science, that 0.00 means something. Now, I know that 1 minute 27.007 point. Let me try this again. 1 minute 27.00 seconds is the same as 1 minute 27 seconds. I know that. But in science, there is something called precision and accuracy. And when you have that 0.00, those 0 zeros mean something to a scientist. So please don't drop them. Okay? So all of your numbers, assuming we didn't go more than 10 minutes, should be to the point something something. Okay? Now here's the other thing. When you took observations, some of you took observations of the hot water, some of you took observations of the cold water, and then I saw some people even like comparing them. Oh, look, this is doing this now, or it didn't do this before. That's good. We want you doing that, okay? But we also have now quantitative observations. We have numbers. And the nice part about numbers, ladies and gentlemen, is numbers make it very easy to compare something. So, for example, which one was the fastest? Which one was the slowest? Why? Because we have numbers here. So it's not about, okay, I think this one bubbled more than the others, or I think this one reacted more slowly. We can actually prove that by looking at our times, okay? So again, in here, rank the variables affecting the time it takes to dissolve from slowest to fastest. So what I'm expecting to see in here is hot water, cold water, room temp water, 7-Up. In some order, that's what we're expecting to see. Those were our variables. Hot water, cold water, room temp, 7-Up. So those four things are what you're going to put in here. And again, you go back to your time. Now, fastest would be the what amount of time? The lowest or the least amount of time. Okay? Slowest would be obviously the longest. Okay? So slowest goes here. Fastest goes here. I probably should have switched that around, but I'm sorry, that's the way I asked you to do it on here. Okay? So again, a hypothesis. Now, first of all, a hypothesis is a what? Kind of. An educated guess. You probably heard that since you were in about 3rd or 4th grade. An educated guess. And in your freshman year, they taught you that a good hypothesis is what kind of statement? If then. Okay? So again, a possible hypothesis for this reaction could involve either changing temperature of the water or changing the type of the water. You don't have to do both. But a hypothesis says that if I do this, then this is going to happen. Now, please think about this for a minute. In terms of this activity, we could change the temperature of the water, correct? Now, when you change temperature, what are the only ways that it can go? Up or down. So when you're saying, if we change the temperature, how are we changing it? Are we increasing it or are we decreasing it? I don't care which one you want to say, but that's got to be the start of your hypothesis if you're doing temperature. If we decrease the temperature, then this will happen to the time. Now, what are the only two ways that time could change? Okay, it can increase or decrease, faster or slower. Basically, ladies and gentlemen, whenever we're talking about numbers, the only way numbers can change is to get what or what?
Higher or lower.
Higher, lower, bigger, smaller, faster, slower, however you want to say it. But that's the only way they can change. So when you write this hypothesis, if I change the temperature this way, then what is going to happen to the time? Is it going to increase? Is it going to decrease? And now you can make an even more educated guess why. You did the experiment, okay? Now, does that mean if you choose to write it and it doesn't match your data, is it going to be wrong? No, because that's what a hypothesis is. It's an educated guess. It may not be right. It may not be correct. But in your hypothesis, if I do this to either the temperature or the type of soda, then this is going to happen to my time. And when we're talking about the then this, increase or decrease, go up or down, okay? Go up or down. Okay. Now, this is where we get to that, what we talked about, or what we didn't talk about yesterday. What is an independent variable, ladies and gentlemen?
Something you change.
Something that you, the experimenter, changes. Something that you, the experimenter, controls. Now, the opposite, not the opposite, but the other kind of a variable is a,
Dependent.
and what is a dependent variable?
Variable that changes based on the independent.
Correct. Now, a variable, just a variable, is anything that changes. Anything that changes. But then we can get a little bit more specific and talk about the independent, the variable that you control, and the dependent, the variable that changed because of it. Now, I know we told you you had to use hot, cold water, 7-Up, right? But you decided which of those you did first, okay? And you decided which one you wanted to do. That is the variable that is in your control. That is the independent variable. The dependent variable would have changed because of those things. So think about that when you are answering this question. Now, there wasn't very much that changed. Name things that were variables to begin with.
Temperature of the liquid.
Temperature of the liquid. What else?
It's liquid.
The type of liquid?
The measurement.
Shouldn't have. We use 100 mils every time, right?
Oh, things we changed.
Things we changed. What was the other thing that changed? The time. Those were the only three things that changed in this lab. We should have used one Alka-Seltzer. We should have used 100 milliliters of whatever liquid. The only things that we actually changed were the temp, the type of liquid, and the time. You controlled some of those changed because of what you controlled. That's the answers for 3 and 4. Independent, dependent variable. Okay? How many of you have ever had Mr. Garai for math? Sorry about that, I really am. Okay? But he and I are fairly good friends, and we spend a lot of time in the summer golfing. And one day he said, you're a dependent variable. He says, I'm an independent variable, which is an odd comment to have while you're golfing with somebody on a golf course, but he's a math teacher and he's kind of geeky that way. What is the biggest difference between Mr. Garai and me that makes him an independent variable and me a dependent variable, other than the fact that I'm much better looking than him, I'm taller, I have hair, and I teach a better subject than he does?
He doesn't have a wife and kids.
Thank you. He does not have a wife and kids. He is an independent variable. He can do what he wants, when he wants, how he wants. I am a dependent variable. I can do what I want, how I want, when I want, as long as I check with my wife and children first. Okay? My schedule is dependent on the other members of my family. I don't get the independence. Okay? I want to go golfing on Tuesday. Sorry, you can't. Your son has a game. You're going to his game. Okay, I'm not going golfing on Tuesday. Okay? That is a dependent variable. My schedule is influenced by theirs. Okay? So again, your dependent variable in this lab is the variable that changed because of something that you controlled. Something that you did. Okay? I wish you all independent variableness for the rest of your life. Okay? Probably not going to happen. All right. So what is a control?
The thing that you're comparing.
It's a baseline for comparison or something that you compare to in an experiment. In this lab, it was the part that we did together that we're going back and comparing to. Okay? So it is the one part of the experiment that I did for you, that we did together. And I said, okay, we're going to compare back to this. That is what the control is here. Okay? A control is something that you go and you compare to. Okay? What is a constant?
Something that doesn't change the experiment.
Something that doesn't change in the experiment. Now, we named a bunch of things that did. Yes, Chair.
So the control was when you did
Yep, which was what?
room temperature.
There you go. There you go. We're always comparing back to that room temperature. Because remember, why are we using room temperature? Well, we wanted to see how temperature affected it. So we used hot and cold water, right? What was the temperature of our 7-Up? Room temp. So again, even though we're changing the type of liquid, then we still had two liquids that were at the same temperature. So that room temperature is always what we're comparing back to. Did using 7-Up cause it to dissolve faster or slower than water? But they both had to be at room temperature. Okay? They both had to be at room temperature. Okay? So think about constants. Think about things in this lab that did not change. Okay? So what are some things that were the same in every one of the 4 trials that we did?
The amount of water.
Okay, amount of water. What else?
Type of container.
Okay, types of containers. Yes.
Alka-Seltzer.
The Alka-Seltzer. Yes. What else? Ooh, got a little more difficult, didn't it? Now, I'm not saying you can't use those 3 that we just gave you, but what else did not change?
The stopwatch.
What do you mean by that?
We didn't use a different stopwatch every time.
Okay, so your equipment stayed the same, and that is a great point. Why? I have 6 balances out on the tables in the back, ladies and gentlemen, and they're really good balances. But I don't guarantee you that if you put something on one balance on one side of the room and went to the other side, that it's going to be exactly the same. I don't guarantee you that if you had 2 thermometers sitting at your lab station and you put both into the same container of water, that they will read the exact same temperature. But if our stopwatch is a little bit off, for some reason, whatever reason, and I use it for every one of the trials, should be off by the same amount each time. Okay? Should be off by the same amount each time. So again, we take that away. Good. What else was the same though? And it has to do with the stopwatch, but not the actual stopwatch.
The unit of time.
Yeah, but we don't need to get that crazy with it. How'd you know when to stop?
When
It's done. How did you know when it was done? Okay, so that's a constant, right? We stopped when the tablet was dissolved. We stopped at the same time. Actually, another constant should have been who did the timing. Because you and I both time it. Your idea of when the tablet is gone and my idea of when the tablet is gone may be slightly different, right? Okay? So again, that consistency that you can do in the lab is always a good thing. Tomorrow, ladies and gentlemen, we will finish up. We'll talk a little bit more about the last few questions. I will talk to you about the conclusion. You can write it, but I will make sure you have everything that you need in it tomorrow before you turn it in, please. Okay? I will make sure you have everything in there before you turn it in.